Okay. So I am Haroon Indrees, and I will be presenting our CVPR 2013 paper titled Multi-Source Multi-Scale Counting in Extremely Dense Crowd Images. So the crowds occur in a variety of situations such as concerts, political speeches, rallies, marathons, and stadiums. And this problem of crowd counting and or density estimation is important from the point of view of safety and surveillance, as it can be used to detect abnormal behavior, and it can also be used to find the volume of commuters, which may be important from the perspective of public transportation infrastructure, and it can also be used to gauge political significance of a rally or a protest. And since turnstiles or human counting is not always possible, we have to rely on computer vision based techniques. Some of the challenges that are associated with dense crowds are low resolution. There are fewer pixels per target, which makes analysis very difficult. Then there are severe occlusions, where many of the body parts are occluded and are not visible. And then there are perspective effects, the change in scale, which makes this problem very challenging. So in order to come up with a solution, we propose two different things. First is we rely on multiple sources and which provide different sources information, and we fuse them later. The second is, since we do not know the correct scale of analysis, we do multi-scale analysis for this solution. And the existing datasets in computer vision typically contain up to 50 people per frame, and these are some of the examples. And they are low to medium density and use temporal information to count the number of people. We, on the other hand, propose a new dataset which has from 100 to 4,500 people per image, with an average of 1,280 people, and in total there are 50 images with 64,000 annotations. These are some of the examples. This is one image. The dotted points are the annotations, and the results on this image are that the ground truth was 634, and we estimated 640 people in this image. Similarly, a few more examples. This image had 1,500 people, and we predicted very close. Similarly, in this image, which has trees and skies also, the ground truth was 673, and we predicted 653. Similarly, some more examples, 2,300 people, and here we have an error of about 200 people. So for the related work, there are two possible ways to count people in an image or a video. First is by detection. We apply some human detector and then count the number of people. One paper in this vein is CVPR 2006 paper here, where the authors get short-term trajectories and cluster them. And the idea is that trajectories belonging to one person will be clustered together. So they count the number of clusters, and that gives a measure of how many people there are. The second approach is counting by regression, where we find certain features and then learn a mapping function directly to the counts. And this CVPR 2008 paper, what it does is finds segment, edge, and texture features, and then they use Gaussian process regression to find the number of people. This paper we also compare against is a NIPS 2010 paper, where the focus is on regions which are very difficult to predict or estimate the counts for, and the authors automatically find these regions while training, and they show that this significantly improves results. So over images, so this is since this is a counting problem, so this can be seen as a spatial Poisson counting process, but the problem is that the density varies, which means the lambda varies. And so this is non-homogeneous and very difficult to model. So what we do is we divide the image into patches, and we assume that the density will be uniform, that is, it is homogeneous, and it can be modeled. So we divide the image into small patches and assume there is one spatial PCB per patch, and which is given by this equation here. So the lambda is the density, and the expected value, or the number of people in that patch, is given by this, where lambda is the density, and this gives the size of the patch. To count the number of people, if we assume that the counts in individual patches are independent, then we can just add them up because of the independence assumption. But all of this assumption simplifies the counts it is not necessarily correct because the counts in neighboring patches are related. There is a strong dependence between neighbors. So what we do is we estimate the counts independently in individual patches and then use Markov random field to model the dependence. So this is the block diagram. We have three sources: head detections, Fourier analysis, and trust point based counts. We use these to get counts in patches, and then we place them in a Markov random field to get counts in the entire images. So the first source is the head detections. Human detections are not feasible because they are not entirely visible. So what we do is we use DPM, deformable path model, trained on NVIDIA dataset. That we take the template corresponding to the head, use a very low threshold, and the detections have scales and confidences. So what we do is we count the number of people given by the head detections, and then we compute mean and deviations of the scales and confidences. So this gives a measure of how reliable our counts are in that particular patch. So these are some of the results. So as you can see, when the heads are properly visible, we get good detections. But there are also lots of false positives and negatives. And that's because we use a very low threshold to get as many detections as possible. And when the head detection fails because the heads are too small, we have to rely on Fourier analysis. And there is one characteristic of the dense crowd, that it is naturally repetitive. So there is a periodic occurrence of heads, as can be seen in this patch. So what we do is we take a patch, compute its gradient, and then take the Fourier transform, apply some filtering where we remove the high frequency and weak amplitude signals, and then find the local peaks in that in Fourier transform, and then reconstruct that patch. So what we obtain is shown here. So we have a patch on the left, and the reconstruction is shown on the right. So for this particular patch, the ground truth was 54, and the number of local maximas here is 195. So as we go to another patch where the ground truth count increases to 102, the number of local maximas also increases to 238, which means that there is a relationship between the two. Similarly, another example, the ground truth count increases to 134, and the number of peaks increases to 254. So this means this direct correlation between these two features is useful, and the number of local maximas in this reconstructed image can be used to predict the ground truth or estimate the number of people. So what we do is we find the number of local maximas, which gives us an estimate of the count, and then we compute mean, variance, skewness, kurtosis, and entropy of the reconstructed patch and the difference patch. Finally, the third source of information is the interest points. And here, what we do is we extract features and build a bag of words representation for each patch. And then we do support vector regression to predict the densities. So, but since not all patches are crowd patches, so it's important to distinguish them from the non-crowd patches from the crowd patches. So what we do is we model each feature as a Poisson random variable. So we model each feature as a Poisson random variable, which is given like this. And so we have a set of negative examples and positive examples. And the negative examples contain patterns which are repetitive but do not contain humans. And then the log likelihood can be given like this. So these are some of the results of crowd confidence. The original image is shown on the left, and the confidence is shown in the middle. So as you can see, where there are no people at the top between the tiers in the stadium or in the sky region with the floodlights, the confidence is very low, which means that it's a reliable estimate whether that crowd is a patch or not, or that patch is a crowd or a non-crowd. Similarly, these are some of the ground truth counts which correlate with the confidence. So once we have these counts and confidences from these three different sources, we fuse them. What we do is we concatenate all of them. This is early fusion. We have 12 from the Fourier, 5 from the head, and 3 from the interest points. And we densely sample patches from the training images. And since we have dotted annotations, we can count the number of people in each patch. And then we use epsilon support vector regression to predict the density. So in spatial MRF, we have an energy function, which is the sum of unary potentials here and binary potentials. Here, the binary potentials will capture the smoothness constraint. And then we pass messages in belief propagation, and where each neighbor tells what other neighbor what the likely states should be, or in this case what the counts should be, and then we compute beliefs in the end, which give us what the counts are in those patches. So since we do not know the exact scale at which to perform the analysis, we do a multi-scale analysis. And here the patches are, this is the bottommost layer where the patch size is small. And then as we go up, the patch size increases as shown here. So the spatial MRF or two-dimensional MRF just imposes constraint between patches in a particular layer. So, but here we have a constraint among patches in different layers. And so what that means is that the count in this particular patch at the first layer should be the sum of counts in these 4 patches here. And similarly, when we pass messages upwards, we sum the counts, and when we pass messages downwards, we divide the counts. So that we infer using the entire graph. And these are some of the results. So these are 3 by 3 patches taken from 3 different images. And the ground truth counts are shown here. So before we use the Markov random field, the count for this particular patch is 31, which is very high with respect to the ground truth. And this is an ordinary patch, as can be seen here. The count should be very similar to its surroundings. And once we use the Markov random field, we get a count of 14, which is very close to the ground truth. Similarly, there are other examples. So this means that the erroneous errors in patches, which can happen due to incorrect predictions, are taken care of by the Markov random field. So for the results, we have 50 images. We did 5-fold cross-validation. And the measures we used were absolute difference, the estimated count minus the ground truth count, and the normalized absolute difference, which is just the percentage error. So for the first, this is one of the images. So here, the Fourier estimated 1128 people, and the head and sift were far below. The ground truth count is 1428. And if we fuse all the 3 sources, we get a count of 1468, which is much better than either of the 3 sources, and much closer to the ground truth as well. Similarly, for the second example, here the head detections has a much better estimate, 1461 people, and after fusion we get 1499, and the ground truth is 1344. So as you can see, the after fusion results get much better. Similarly, for the third example, the sift has a much better estimate than either of the Fourier or the head, and is much closer to the ground truth. And similarly, the fusion is still better than either the sift or the Fourier or the head detections. And these are some of the numbers. So if we just use Fourier, we have a very high error of 84%. And when we add confidence, it goes down to 41%. And absolute difference goes down to 522 people per image. When we add head detections, we get a further reduction in absolute difference. Then when we add sift features, we get a reduction of 10% in percentage error. Similarly, when we use Markov random field, we get an additional reduction in absolute difference, which goes to 419.5 with a percentage error of 31.3. We compared against 2 methods. The first is this ICCV 2011 paper, which is primarily based on head detections, and it has a much higher error both in absolute terms and percentage terms. The other paper is what I described earlier, the NIPS 2010 paper here, and it has a much better absolute difference, but has a very high percentage error, and I will describe why this is the case. So this is the per patch analysis from the different images. The images here are sorted according to the number of people. So the first image has the fewest people, around 94, and the last image has 4,500 people. So it can be expected that as the number of people in the image increases, the error also goes up. And this trend can be seen with these statistics which show the mean in that image. And this is the percentage error. And what's striking here is that the percentage error is lowest in the middle range here, and it's high at the lower end, low density, and high at the high density. And the reason for this is that the largest count here is almost 5,000% of the smallest count. So when we are trying to balance such a wide range of densities, it kind of favors the middle range. So here I show the percentage error decomposed into different groups. And the groups are again sorted according to the number of people. The first group has smallest, fewest people, and the last group has the most people. And here I show the absolute counts, the absolute number of people that were output by the individual methods. The black curve shows the ground truth counts. As you can see, there is a linear trend here. And so the ICCV 2011 paper by Rodriguez et al., it has a very high error at the lower end and similarly higher error at the higher end. And the reason for that is evident when we look at the absolute counts predicted by this method. The curve is almost flat. That is, it doesn't respond very well to the change in densities. Similarly, this is a NIPS 2010 paper, and it has a much better, it adapts much better to the higher density counts here, but has still a higher error here, and that's why these green bars are so high. And finally, the proposed method, which has a very consistent error rate throughout all the densities, and it is visible here. The blue curve follows the black curve very well, except for this last group, which is difficult for all the three methods. And this is one image from that group. And so the ground truth counts were 4,500, and we predicted 2,500, as did the other methods. And so the reason for this is that these images were high resolution. So when we were annotating, it was much easier to annotate them than their low resolution, high density images. So they naturally had more number of people in them. And so the number of people in this group is very high. The general trend is linear, as can be seen here among the first 40 images, but in the last group the counts increase super linearly. So when we are doing regression, these kind of become the outliers and are difficult to predict. And then humans become also small and similar, so SIF features also have very difficulty in discriminating among the different patches. So in conclusion, we introduced a new data set which has 50 images and 64,000 annotations. And we used multiple sources, and we showed that they are complementary in nature. And we used multiple scales in the form of Markov random field, and we showed that also improves the results.